So, once again, we are live, and good afternoon, Anna.
Good afternoon, Francis, again.
How are you doing today?
Very good. Thank you very much. How are you?
Yeah, I'm doing great. Great. I'm waiting to finish our lectures with you, and then I probably will join the party for the teachers.
Oh, that sounds very good. Unfortunately, I'm not there with you. So
Yes,
get a beer for me, okay?
sure. So today, with basically, we are talking about energy, and that is the one of the most pressing concerns for IoT devices. And I guess Anna has some more uh, insightful presentation for us. So, welcome, Anna.
Thank you. Thank you very much. So let's see whether I can answer all the questions. I actually doubt so because energy is a huge topic in IoT. We already started with some discussions yesterday, and there were also some questions even on Monday, I think, when we were discussing also sustainability issues and energy costs and so on. So the topic is really huge, and I will try to give you here a small overview of where you actually spend your energy in IoT, like where exactly, and how you can save energy, of course, and also what kind of energy sources you can actually use for IoT, because this is also not completely straightforward. So let's start. First of all, it's important to mention here that we are looking at an energy consumption from the IoT device edge perspective. Of course, you could also look into energy perspective and energy issues at the cloud or, for example, at the gateway level. However, we're focusing here really on the edge devices because those are the ones which are, let's say, the most of control for us. And let's say the most interesting because we're at the end an IoT area. Everything which has to do with the cloud or with gateways and so on is out of topic today. It's just too much simply. So, where do you spend your energy in IoT? Here I have two examples for you. The left example here, MoleNet, is our underground sensor networking platform, IoT platform, which I presented to you already on Monday. It is an underground sensor which you can bury down to 50, 60 centimeters below the earth, and you can send the data wirelessly out of it without burying it out, without putting the antenna out. And so here we did some measurements with our device of how much, what is the current draw during different activities of our sensor. So here, for example, you see that obviously we're sleeping, everything jiggles around zero. Then obviously we wake up again the IoT device, the sensor node. And sending and storing is exactly this whole event here is sensing the soil moisture and then storing it locally on our SD card on external memory. Then you continue more or less equally until you manage actually to transmit your data. That takes always a little bit of time because the radio has to warm up pretty much, has to prepare the medium. Sometimes it takes also some time to back off the channel and so on and so forth. So at some point you manage to transmit your data and then you go back first to a little bit of more processing and then you go back to sleep. First of all, this sleeping cycle is something which will be keep returning today too. It's a very important concept in IoT that you sleep. Exactly as for humans, for us, it's also very important that we sleep. And for IoT, it is the most effective way of saving energy. So whenever you don't really have something to do actively, you don't keep your components on, but you put everything down to sleep from which you can self awake again. This is a very important property too. We'll be coming back to that many times today. So if you look into a specific, so with other words, here in the MoleNet platform, you see that, okay, sensing and storing takes some energy, not that much compared to a transmit event. However, if you look also a little bit more, you also figure out that, okay, but this event here, especially for storing something, takes longer. And the transmit event is one small, very short peak. So it's a very high peak, but at the end, it's very, very short one compared to this whole sensing and storing events, which are much lower in absolute values of the current drone. but they are much more, but they're much longer. So another possibility to look into this story is to check a specification sheet. We were talking yesterday about specifications for sensors. The same specification sheets also are available for your low Pis, for your 5Pis, for Arduinos, for all possible platforms. Like whenever hardware you buy ready from the market, you get a specification sheet with it. And so here, for example, we have taken the so-called Z1 sensor node, which is something which it's coming from Zulercio, it's a Spanish company. They're still pretty well presented on the market. It's a simple sensor node, which you can use pretty much as any other IoT device. It was called sensor node because it's more kind of coming still from that time when we're calling them sensor networks and sensor nodes and not that much IoT. So if you look into the specification sheet, you see the main components which we have on this platform. It's the microcontroller. In this case, it's not a ESP32 as we are kind of today have it most of the time, but it's the Texas Instruments MSP430, also very, very popular microcontroller. Then we have a radio transceiver, which is in this case the so-called CC2420. It is operating at 2.4 gigahertz typically, but it can operate also at lower frequencies. We have an accelerometer on board. We have an external flash. This is this external memory, SD card, whatever you would like to call it. And we have a temperature sensor. So let's explore a little bit here. First of all, the modes, and then the current draw. So the mode means that you have not only simply the component, but you can run it in different modes. So for example, a microcontroller can be active or sleeping. The radio transceiver has even free states, free modes. It can either receive something, so being up and listening to the medium to receive something. It can be actively transmitting something, and it can be sleeping altogether. So during sleep, no transmission is possible. Not receiving, not transmitting. The accelerometer can be in a standby or being active. Standby, pretty much, it's not really like a sleep, but this is an accelerometer, something which you have actually to actively switch on. Otherwise, it takes simply too much power. The external flash also has free states. Either it's sleeping, so you have to wake it up in order to do something with it, or it can write or read from the memory. And the temperature sensor can also sense or sleep. And so for each of those modes, we have an associated nominal current draw, which means that typically, normally, statistically, over many different devices, this will be a number which is possible and it's okay. You can expect deviations, like you should not expect that you will really measure 1.8 whenever the microcontroller is active. It can be significantly more, let's say by 20-30% even. But this is approximate numbers. So if you look into these numbers, some interesting things become obvious. First of all, let us look into the radio transceiver, because this is the one which we identified at MolNet to be the most power-hungry peak which we can observe. In the ref transceiver, for receiving something, you need 19.7 milliamperes. For transmitting, you need only 17.4 milliamperes. And for sleeping, you have 0.01 milliamperes. So obviously, sleep is a very good idea if you don't have to communicate in any way. But it's a very interesting question why actually receiving needs more current, more energy, more power than transmitting something. I like to explain that with the following, let's say, association. If you're in a crowded room, imagine you're in a crowded room and you're trying to talk to somebody. When you speak, okay, you have to raise a little bit your voice maybe, but at the end you can ignore what is going on around you. You don't have to listen to the conversations around you, but you focus on your own voice and just speaking out whatever you need to speak out, right? You say this and that. However, if now your conversation partner is answering to you and trying to tell you something, then you really have to focus, because all of these conversations are coming upon you and you have to focus and to concentrate on this particular conversation partner and to filter out the conversations which are around. Exactly the same is happening for a transceiver. Not exactly in the same way as we do it. It doesn't have ears, but it has an antenna. And on this antenna, it receives many different signals. So a wireless signal is never alone in the environment. Like that will be perfect, but that's never the case. You have also background noise, for example, radio cosmic activity. You have normal environmental noise, which is also wireless. It's the interference is coming also from microwaves. It's coming from all of our devices, smartwatches, all possible remote controls, everything. And so your transceiver can focus on a specific frequency band, but it doesn't mean that this frequency band is also kind of empty and only your own packet is arriving there. But you receive many, many different signals in this frequency band, and the transceiver has to filter them out to compare their quality, their strength, and then to kick out everything which is not relevant to in order to finally decode your packet. So with other words, you can really consider that that transmitting something is slightly easier than actually receiving something. Okay. Sometimes this difference is very tiny, even not even negligible, but sometimes the difference is not that small. Okay.
So basically, when you are talking about sleep, are you referring to deep sleep, or I mean, what kind of sleep it is?
Okay, typically we differentiate between the so-called, well, it's a tricky question. Typically, we really have sleep and deep sleep.
Mhm.
With sleep, we typically mean, and then there is something which is called a standby or wait. This is not a sleeping state at all. Okay, this means that this component is actually up and running. It's kind of a standby, but it doesn't do actively right now anything. But it's completely awake, and it actually needs a lot of energy again. So when we're talking about sleep in microcontrollers, typically you have these two states, sleep and deep sleep. And sleep is something which needs a little bit more energy than deep sleep, but significantly less than an active one. And the good thing about the sleep is that you can self awake. So you can continue counting the ticks of the microcontroller and say, after 10 minutes, I would like to wake up. And the microcontroller can handle that by itself. If you go into a deep sleep, it means that you pretty much shut it down.
Mhm.
And it is not real. Typically, microcontrollers cannot wake up from that from alone. They have to be triggered from the outside with an outside component. That could be a real-time clock. It could be another radio. It has to be another component which actually wakes them up again. But the problem a little bit is that you have to be careful with how manufacturers describe those states, because some of them say deep sleep in order to make some sort of a case that, oh, it's very energy efficient, but it's actually a normal sleep. And sometimes they say just sleep, but they actually mean that it's already switched off. So in each specification, again, you have to check very carefully how exactly the sleeping states are defined.
Mhm. Yeah, good to know. Yeah,
Yeah.
thank you.
So, if we compare now the radio transceiver and its energy requirements to the other components we have, it becomes clear that, okay, for example, the external flash is also a very energy hungry component. It needs 15 milliamperes to write something, only 4 to read something. This is a little bit better. And it has also sleep state from which you can be waken up from the microcontroller at any time, which is obviously a very good idea to use. If you look into the sensors, let's say the accelerometer and the temperature sensor, it becomes obvious that it doesn't matter, right? If you compare their energy consumption, it is so small that even if you forget or you decide not to put your sensors on sleep, that has only a very insignificant impact on your total energy consumption. And the microcontroller itself is also actually very efficient, let's say, with 1.8 milliamperes. This the active state. It is lower than any other of the active states of your other components, so you should not bother too much about your microcontroller. The important things are the radio and the external memory and some sensors. Of course, you have to be careful. Those two sensors are very simple. We had that discussion yesterday. Temperature and accelerometer are simple passive sensors. If you go for a camera or a GPS, they need significantly more energy. So the message here is always know which component needs what kind of energy, like not only what kind of input voltage, which was the issue yesterday. Now we are more interested in the energy consumption and to see whether we can put them to sleep, because sleep is our main joker, if you want, if you would like to save energy.
And this energy profile is only for a specific example, right? It's not general.
It's
Someone
not
was
general.
asking.
The profile, the absolute numbers are absolutely only for one specific hardware, but you can expect similar numbers for other platforms. Like you can expect again that the radio transceiver will be very energy hungry, that the microcontroller will be perfectly fine, simple sensors will be perfectly fine, external flash will be hungry. Okay.
And there was also another question about sleep mode. So, is sleep only used in the context of lowered energy consumption, or does it also affect the longevity of the device when used a lot? Or
I would not say that it has an impact on the longevity of the device. The problem is that the longevity of the device is not that much dictated by energy consumption or active usage, but by environmental impacts. So if I leave my IoT device outside in the rain, it doesn't matter whether it's active or not. At some point, it will just the materials will actually start suffering, and it's not a matter of how much you use them.
Mhm.
Maybe there are some exceptions to that. Happy to discuss something weird, some examples, something concrete. But in general, I would not say that this helps you keep them online in some way. So, what kind of energy? So, we were talking about where do we spend our energy, right? Now, the question is where do we get the energy from? Because not always wall power is available. So, wall power is definitely one of the possibilities, and this is very comfortable if you have access to it. So, if you have some kind of a factory setting, industrial setting, building setting, smart home, and so on, where wall power is kind of given there by default, then of course you can use it, and this is a simple and efficient way which you shouldn't even consider something else. Of course, there is also the possibility to use batteries. You can also use some sort of a direct connection to an energy source. What do I mean by a direct connection? That some like there are two possibilities to connect the so-called energy harvesters, like thinking about a solar panel. You can either directly connect it to your device, which means that whenever the solar panel is producing energy for you and the input voltage is high enough to power up your IoT device, then your device will be powered and you can actually do something. This is sometimes very useful if, for example, the energy harvester itself is actually serving also as a sensor, but this is rather an exception. So imagine I would like only to send data if the solar panel is producing enough energy. Otherwise, I want to keep silent. And then you can connect it directly, and then you don't need any kind of intelligence, just power up with your sensor if you want, the light sensor, which is in this case a solar panel, and then you know that it will be working automatically. But as I said, this is a rather exceptional situation. Typically, you have an energy source which is connected to a battery, which is storing the excessive energy, which you can use then later. So you put a battery between the solar panel and the IoT device so that the solar panel actually just charges the battery, and on the other side, you use the battery as your energy source. As I said, there are some advantages and disadvantages of these two versions. It's cheaper to not have a battery, And it might be also more long living. Some people are obviously very interested in that, because the battery is actually something which fails very quickly. So if you remove the battery altogether, your whole system might actually become a little bit long living. But I don't think somebody has real experience yet with really long living IoT devices, because we're changing them and improving them and optimizing them simply too often right now. So what kind of issues you have with energy in IoT? One is, first of all, that the energy source which you selected is not necessarily available. So, for example, outdoors, you don't have wall power. Large infrastructures like an airport or a large storage house, they might also not have wall power. It looks like a building, but they might not have wall power for you. Mobility, of course, is a big issue, because even if you have wall power, for example, if you would like to enable some sort of a mobility or even flexibility to change the device, to put it in another room, to carry it around, then of course you cannot use wall power anymore, and you have to use something else, either a battery or an energy harvester with or without a battery. Another problem, of course, is that batteries simply deplete or fail, which means that whenever you would like, for example, to install a battery for an outdoor application, after some very short time, your batteries might fail. So they might deplete simply and you have to exchange them, or they simply fail because this is simply a very, very failure intolerant component, let's say. And this issue has to be always considered, whether you can actually exchange your battery easily and whether your system is protected, for example, against battery leakages, because those are chemically very aggressive and they can destroy your complete system. So, for example, when we are deploying our MolNets, our underground sensor nodes, this is a big issue, because I actually cannot go and anytime exchange the battery, because I will disturb the soil, I will disturb the plants which are growing there. So this is an issue that's why we're very interested in very good energy efficiency, and we're going there to extremes compared to, let's say, somewhere on a fence. You remember maybe the wolves, where people are going there checking the IoT devices anyhow every couple of days, and changing the battery is not that much of a problem. Like, it's nasty, it's costly, but it's not really a problem. So let's come back to duty cycling and sleeping.
So,
Yeah, sorry. Yeah.
yeah, I mean, before going into another titles, I'm just wanted to pick up a couple of questions here. So one was about one of the slides that you were talking about different components and their current that they are producing or consuming. So the question was, can we, or is there any way that we can measure energy of these individual components?
Yes, what you can do is the same what we did here for the MolNet, but it's not that simple. It is like, what you do is that you connect simply your complete platform, your device, to a voltmeter, which has also the possibility to either to immediately graphically represent or to at least save the numbers and not just show you a number. Those are, well, quite expensive equipment actually, but any university with an electrical engineering department should have those in tons. And what you do is exactly what we do here, that you implement a special program which is very well, like, it's not something messy, but you go very systematically from sleep to then sensing, storing, then sending out, and then you sleep for a long time again, so that you can easily track where exactly your program was actually active, and then you can recognize actually which events are what. It's not a very exact method of doing it, but it's a very realistic one, because you know then exactly which events, which processing in your platform actually uses the energy, consumes the energy.
And then, since you were talking about solar panels, there was a question about the hardware. Like, can you suggest any small scale solar panel devices that can?
No, no, right now, especially with this crisis of electronics. They're changing so fast. I cannot even keep track of them, and what is available in Germany might not be available with you,
Yeah,
and vice versa. This is crazy. You can try to check pretty much the recommendations of people in various websites, because those components are bought typically by nerds like we, and then you can get a pretty good recommendation of what to use or not. But they're changing so fast. Sorry.
yeah,
Okay, so let's go to duty cycling again. I didn't call it duty cycle before, but this is actually the scientific term for that. It is is simply saying how we call sleeping. When we sleep, it's important that we don't sleep randomly. Like, this is also a possibility, of course, to randomly sleep and to sleep as much as possible. But then you have to make sure that your communication can cope with that. I'm sure that Marco will be talking much more about communication and how to synchronize those. The duty cycle is defined very easily. It is simply the time which you are active over the complete period. And please note that it is not something like, for example, here in this example, let's say, we have a zero point 0.1 second you were active, so sensing, storing, sending, processing, and so on. And then you went to sleep for zero point 0.9 seconds. So if you calculate this duty cycle according to this formula, you have something like zero point 0.1 divided by zero point 0.9, which is exactly, by 1, sorry, which will be exactly 10%. So 10% of the time you are on and doing something. But please take care that it doesn't tell you how often you actually go to sleep. Okay, so I can change here the period and I can still be active for only 10% easily. But the period itself disappears in this formula. And this is also not what we're interested in. Like, the period itself is dictated by the application. For example, if I'm into agricultural scenario, it is more than enough to measure everything every half an hour, because nothing interesting will be happening in between and you don't want to waste your energy. In some extreme applications, you even measure once per day. In some other applications, let's say a security camera, there you have to measure pretty much the whole time. And then there are some in-between applications where you measure pretty often, but also not the whole time. So this duty cycle is telling you pretty much of how much of the time you use for active doing and how much of the time you try to save energy. And this number is important. Like, 10% is already a lot. We typically target values to very few percent, typically below 1%. This is what we target, and this is what is considered a really good value. Okay. So how to save energy? One possibility, and the best, is to sleep. You can do duty cycling and sleeping. And the good news is, I have one good news and one bad news for you. The good news is that for microcontrollers, this is all included. Like, you get it for free. You just say sleep, pretty much, and then you know that you're sleeping, and you can put also wake up function, and it will wake up after some time. This is available for your 5Pis, low Pis, Arduinos, and so on and so forth. However, for embedded PCs, so we're getting a little bit up now let's say, the architecture, and maybe starting thinking about gateways. There, in embedded PCs, this is not readily available. So, for example, if you get a Raspberry Pi, it is not there. So if you can switch it off, but you cannot wake up from alone anymore. So you have here two options. Either you can use a microcontroller, which is connected to your Raspberry Pi, and use the microcontroller to wake up your Raspberry Pi, which is one example is here on the right. This is called Sleepy Pi. So Sleepy Pi is just ready to go electric circuit which connects the Raspberry Pi with the Arduino. Here's the Arduino, here's the Raspberry Pi. with a real-time clock. This called RTC, is a real-time clock, and so those two can, like the Arduino, can now wake up the Raspberry Pi. And this diagram here is available free online on this link, and everybody pretty much can use it who likes to use it. The other possibility is to use something simpler than an Arduino or a microcontroller, and to use only, for example, an RTC, an external timer. Then the important thing is that you need an electric signal which wakes up your Raspberry Pi. Otherwise, it doesn't work. It cannot wake up from alone. So any kind of an electrical component which somehow decides to wake you up is then able to do that. There are also, for example, the so-called wake-up radios, which is a very simple radio at very low frequencies, very energy efficient, which waits for a signal which just says wake up. There is no data on this signal. There's just a wake up signal, but that radio, with the wake up radio, can now wake up your Raspberry Pi. This is also another possibility.
So there was a question also about waking up, and I guess based on your information, it's possible for low Pi and 5 Pi devices, but not for Raspberry Pi devices. So the question was, can we use some kind of rule for waking up if based on some sensor values, like using some thresholds and so on?
Not sure that I fully understand the question, but typically you do not I'm trying to think about an example. Okay, typically, let's try to answer it this way. Typically, you don't connect your sensing logic to the wake-up logic. So, for example, in agriculture, you say every half an hour, I want data. What the data is, I don't care. Like it's simply sent to the cloud, or I do something, or I actuate my sprinklers, whatever. But I don't connect the logic with each other. You could do that, of course. You can say something like, well, if the sensor starts changing very quickly, let's say I wake up, I check my temperature, and it was really different from the last reading, I can say, oh, something interesting is going on. I will increase my duty cycle. So I will wake up a little bit more often in the next time to be sure that I don't miss anything interesting.
Okay.
But this is kind of an implementation logic. So especially in microcontrollers, this is really like a normal program loop where at some point you simply say sleep. And then you wake up again, but you can put the timer just before going to sleep. You put pretty much your timer and then go to sleep, and then the timer will wake you up. And you can put this timer for the same amount of time or for different amount of times. That's your logic.
Yeah.
Okay.
Yeah, it was a good question. Yeah, thank you.
Yeah, thank you. So another way of another important, let's say, skill when you are deploying real applications is to enable or to learn how to do a little bit of energy modeling. I know that it's becoming now a little bit math here, but sometimes math is actually very useful, and it's simple. I can promise you that one. So what is energy modeling of IoT devices? Typically, based on those measurements or on those specifications, which you have seen in the first slides, you pretty much can do your own energy model by saying, okay, the total power of the device is a sum, very simple sum, between the power of all sensors and actuators, the standby power, the power for the microcontroller, including data processing, and the power for transmitting, let's say, to the gateway. Okay, so with other words, you put all of your components which you have on your platform, and you don't forget anything. You don't forget the microcontroller, for example. You put them together, and you say, well, at any point of time, I actually have a sum of all of them. That's good. And here we have a small example, which is coming from reference one, which is on the last slide. You can check it out later. where people have done the exercise to say, well, I'm sensing, I'm transmitting, I have some wake up phase, and I have a standby phase. So you kind of dissect your program into different phases. Exactly as you have seen it there in the first slide with MolNet, I had a sleeping state. I had a phase where I'm sensing and storing, and I had a phase where I'm transmitting, then maybe doing some data processing, and then again sleeping. And given the duration of each of those phases, and the current which they need for each of those, you can calculate the power which is dissipated over this complete phase and then sum it up. Okay, and this is an energy model. So for each kind of an application, so for each individual hardware platform and for each of your applications, you can derive such a simple energy model, which looks a little bit nasty because you need lots of information and measurements and data, but it is mathematically very, very simple. And how to use that now is the question. First of all, before we go into how to use it, there is a small trick. Like you need to know which phase is occurring how often, right? Otherwise, you cannot do anything with this model. So there are two, let's say, two main ways of implementing your sensing application: the so-called broadcast mode, or what we typically say periodic sampling, or the so-called event-based sampling. Let's look into those, what they are. In broadcast mode, the idea is very simple, and you have seen it already many times. I just repeat the same thing over and over again. I sleep, I sense, I store, I transmit, I go back to sleep. And I do that absolutely regularly. I march through time. There is no differences. I don't use any other weird logics. I don't connect the sensing to the wake up logic and so on. So this is the simplest possibility because your energy model becomes also very simple. You simply know for each of those periods how much time you spent in each of your phases, and then you have the complete model. It becomes a little bit more complex if we talk about event-based sampling. Event-based sampling is to say that I actually wait for a sensor to trigger the sensor node. So for example, I wait for a camera to detect some movement, and only then the microcontroller will wake up, start storing the data, maybe even processing it, and then sending maybe to the cloud. And the problem is now that I don't, like, once I'm triggered, like this is this event here, this trigger, once I get triggered, I know what will happen, right? Because I do always pretty much the same thing, right? Like I simply get the data, I store it again, I send it out and so on. Then I wait for the next trigger. The problem is that now you don't know how often this trigger is coming. And in order to make such an energy model, you need some sort of a mean value. How often do I expect to have movement in my garden during the night so that the sensor will be actually active in doing something? So I pretty much need to know how many cats are running around here, right? And how often they will activate my security camera. If it is something like an accelerometer, for example, you have a bridge monitoring application and you would like to put an accelerometer, and if that exceeds some values, you would like to get active. Then you need to also to know how often does that typically happen. Why do we do all of this stuff? The reason is, maybe I have to explain that before going ahead. The reason is that you would like to predict how long will your application survive. You have some batteries, you have your platform, you have your implementation, your application, and you would like to predict, am I going to survive with that for a week or for a year? This is important, okay? So that's why we're doing all of this. So when you compare now periodic against event sampling, as I already said, In periodic, the pros is really that it's very simple. You march through time and there is no difference to the application, what is happening, what kind of data you have, and so on. The disadvantages of using a periodic sampling in general is that you might actually miss some important measurement, or you might send also duplicate data because, for example, nothing has changed since the last event. So, for example, if I'm sensing, let's say, an agricultural scenario every 15 minutes, I actually might miss some small rain or something else. Or I could be measuring exactly the same over and over again because it's, for example, during the night and nothing interesting is happening and the temperature is staying the same. Then I will send duplicate data because simply the data is the same as last time. So that is a little bit kind of triggered then by the event-based applications when you only send data if something interesting is happening. The good thing is about that you only send really important data and you save on transmissions. And you can also, you're a little bit better at not missing important stuff. The problem is, of course, that to define actually what is interesting, so it could be that you defined it in a way that at the end you get too little data and you again miss some important events. Um, and this requires simply a very good model, a very good understanding of your events. So that's why periodic and event sampling are kind of the two really main ways of implementing your IoT applications. But you have to consider them carefully what exactly you need and how well you understand your system. Typically, if you don't understand your system very well, I would definitely start with periodic reporting because it's safer. Okay, I gave that example many times already. So, for example, periodic would be simply send the temperature every 10 minutes, or event-based will be train a model what is a normal temperature during day and time, and then send the reading only if there is a difference between this expected temperature or the reading, the current reading. That will be a simple example. So, back to energy modeling. Any questions so far?
Not about the slides, but there was a question about the course requirement, like if students need to do the energy modeling for their projects. I said no if they don't want to.
Okay, you managed already this. But I would say whoever does it gets some bonus points.
Yeah, that's of course for the higher grades. Yeah.
Yeah, exactly. So we are into energy modeling back, and we would like to discuss now the precision, because this is something which should already start ringing an alarm bell in your heads that, is that simple model really good for us? And can it really be of any use? That's correct. It's a very simple model. They exist, of course, much more complex ones, but let's not bother about them here. So I do not take, for example, any battery properties into account, right? I simply assume a battery is kind of a bucket full of energy bins, and I can take them one by one and use them for something. So this is not very realistic one. Of course, such a model, the results of such a model will be very imprecise in absolute numbers. So I will predict at the end something like a lifetime of my device system, 17.5 days, right? Because I'm jiggling with numbers. And at the end, I will get something which looks very precise. But it's not. And the absolute numbers are not important. And you should never really take them very seriously. However, it is very good in order to compare different implementations against each other. So imagine you would like to compare two versions of your application, and maybe they're a little bit more complex than what we have been discussing so far. Maybe there is a possibility to always periodic send something, but only if it's something interesting, send the data. Or maybe there is even the possibility to gather some packets first, like some readings, and then send them in one compressed packet, and so on and so forth. And so for such questions where maybe it is a little bit more complex, the implementation, you're not completely sure whether you now saved energy or it was for nothing and you just complicated the complete system, then it's good to use such an energy model, because that doesn't lie to you which one will be now more energy efficient than the other. And again, some normal comparative rules apply. So if they're almost the same, let's say one is saying 17.5 days and the other one is saying 18 days, they're the same. I would not even bother looking into the more complex implementation then. But if one is saying 17 days and the other one is saying 56, oh yes, this is a big difference. Okay. And very often this doesn't become, for example, obvious, especially with event based. Because event based sounds first that, ooh, but many things can happen. Like maybe a cat is running around the security camera constantly and constantly has to do something. In such a situation, of course, you need very good realistic data and to first measure how often really your events are expected to happen. But it's surprisingly low at the end. So that's a very important hint, simply, that whenever you would like to use such an event-based system, don't drop it too fast. It can save a lot of energy. It really depends on the events which you're hunting.
So, is there any difference between energy modeling and power profiling, let's say? Um,
Yes, it is. Power profiling is what we did in the very beginning. You profile one single period. You understand how high is the power consumption of each individual phases or events or processing steps. This is power profiling. So you profile to understand what consumes your energy, for how long, and so on. Energy modeling is a long lasting model. So it calculates at the end the total dissipated power for a very long time. And so you start there with a power profile that is the input to the energy model, but then you calculate the total lifetime.
mhm.
Okay.
Yeah, it's good to know, I think. Yeah, thank you.
So here we did an experiment just to tell you a little bit more about precision of energy modeling. Again, we have the same table for the Z1 node components, and we did an experiment. We calculated with an energy model what would be the energy consumed and how long we expect our lifetime to be at different duty cycles. So if you look into this graph, we have a duty cycle of 25%, very high, very unrealistic, to be honest, but otherwise we'll be waiting too long. So we decided to make the experiment a little bit more fast. Then you have a duty cycle of 75% and you have a duty cycle of 100%. And so this green line here, the dotted green one, is actually what the data sheet, let's say, with an energy model and with the data sheet specifications, what we calculated. So at 25% duty cycle, we calculated that the lifetime of our particular application will be above 500 hours. Okay. Then for 75%, we calculated it to be somewhere between 150 and 200. And then from 100% duty cycle, so on the whole time, no sleeping at all, we calculated it to be like something like 140 hours. And then we run some real experiments and we left the sensor nodes to die, really. And then we measured this time. And what we discovered, of course, is a big discrepancy between the specification and our simple energy model and the real value. However, what you can also see here is that, of course, the let's say the tendency is the same. So the energy model is able to take into account that with some that with higher duty with lower duty cycles, sorry, that with lower duty cycles and more sleeping, we will be saving more energy than if we don't sleep at all, and in between is a 75%. So, with other words, again, I would like to stress that do not trust the absolute numbers, but use them always in comparison to each other. Okay. So, a little bit about the energy consumption of sensors. As we said also yesterday and today many times, simple sensor have some sort of a on-off consumption, which is available in data sheets. You just check it, you know it. It's a little bit more complex if you start getting into a camera. And here I have a very nice example for you just to understand what's going on here. This is again coming from this reference one, which you can check later. Here, the authors have measured the power consumed of a camera depending on the frame rate, which they have set as a parameter, of course, of the camera. And then they they measured it in two different situations. One was to connect the camera to an Ethernet. The other one is to power it with Wi-Fi. So Wi-Fi will obviously use more power. It has a bigger energy consumption than using Ethernet. And so what we have here is that depending on the frame rate, of course, the power starts growing because it's more precise, let's say, right? Like the quality is increasing with the frame rate. And so the power does so also. And if you compare it now to Wi-Fi, you see that, of course, Wi-Fi is much more power consuming than with Ethernet. And so the whole story moves here up. Okay. So this is just to understand also a little bit the energy consumption of sensors. Of course, also the same connection exists between different wireless protocols which you can use. So in this example, maybe at home you can try a little bit to analyze this a little bit more in detail. Here the authors again have explored Bluetooth Low Energy, Zigbee, Wi-Fi, and RF433. This is a simple radio transceiver at this frequency at 433. And they have identified their different modes and how much, so the transmitting, receiving, wake up, idle, sleep, and so on. And here they have also identified how much time each individual phase is spent by the different protocols. And so if you explore those graphs here, it becomes obvious that, for example, Bluetooth Low Energy has a very good power consumption line compared to Wi-Fi and normal Bluetooth, which are very power hungry. And these two, this is for event driven, and this is now for broadcasting. Polling is an application which we haven't discussed yet. I'm sure Marco will discuss that in the context of LoRa with you. Polling means that the gateway polls the sensors in order to give it data, which means that the device itself, the edge device, has to be awake the whole time. So it's a very power hungry mode, which we typically don't use. So if you analyze this a little bit at home, it's quite interesting really to see how the different wireless protocols perform in those three different applications, and using a very simple energy model at the end, but it's actually very realistic here. The results are definitely covering with what we know also from real experiments. So how can we save energy? We can sleep as much as possible. This is something which my students typically like a lot as a general suggestion, just sleep as much as possible. You have to also try to avoid continuous listening or polling and stand by. Like try to sleep simply, like avoid system designs where some devices have to stay online the whole time, because either you're wasting energy, even if you're on wall power, you will be simply wasting energy. If you're on battery, you really waste your time. You can use energy model to predict coarse energy consumption in order to understand better your system before you actually deploy it. And you should really plan very carefully your communication pattern. Like, is it event-based? Is it polling? Is it periodic? And you should always switch off all non-used services and hardware components. For example, the external flash or some sensors which are currently not needed. You should always shut them down. Sorry. I will try to go very quickly for energy harvesting because we have another lecture at 7, right? Okay, so I will go very quickly for that. I didn't want to go into details in this section anyhow. So there are some ideas for you, which you can research on your own pretty much to see what is there and what can be used. And there are some very cool projects about that. It's really worth looking yourself. One possibility is wireless power transfer, which pretty much means that radio frequency energy harvesting devices are used, and they can convert electromagnetic energy into usual direct current, and which means that they can do something with that. So RFID is a simple example of that. You can use, of course, solar panels. Typically, combine them with battery. We have discussed them already quite a lot. You can also use thermal energy harvesting, which is quite interesting because you can harvest energy from differences in temperature, either over distance or over time. So, either something which gets hotter or colder over time, or in distance. So, for example, when you go deeper into the earth, it starts getting warmer, and you can harvest energy out of that, which is pretty nice. You can also use piezoelectric energy, which means that you use mechanical energy. So, for example, when I'm moving, or when I push a button, or when I step on my shoe, I can actually use this as an energy harvester, and it's called piezoelectric. I think we will skip simply the intermittent computing. You can maybe check it at home, and if you have any questions, I will be happy to answer them. And instead of that, I would like rather to give a little bit of time for some questions here.
Not many new questions until now. I think I covered all the questions so far.
Okay, then let me tell you maybe for 2 minutes what intermittent computing is. Intermittent computing is a kind of a novel programming concept to cope with intermittently powered devices. Intermittently powered devices are those who we discussed in the very beginning, which are connected directly to the power source without a battery in between. So whenever I have energy, I can do something. Otherwise, no, I switch off immediately when the energy is not enough. And such operating systems even exist already, like, for example, Mementos, CleanCut, HarfOS, who are doing that. They're doing this, and they're using typically atomic operations. So if you are a little bit more, let's say, knowledgeable in the area of software engineering, and especially of concurrent programming, you know what atomic operations are. Those are, we have been discussing them yesterday also shortly, that those are processes which they're small pieces of code which you isolate from everything else in order to signal to the platform, to the CPU, that you have to do that first completely before moving to the next piece of code. And in this way, you can implement such whole operating systems and applications where you simply say, whenever I'm being interrupted, I can revert to the last state and just start again from there. If you have more interest into that, you can check this reference too. It's a very nice explanation of those. These are these two.
Yeah, maybe I can pick one more final question from Discord. I tried to answer already, but probably you have a better answer than me. So it was about the difference on sleep and wake up in the context of sending data, collecting data, transmitting data, and so on.
Difference between sleep and wake up?
Yeah. So
Well,
I guess.
sorry, I don't understand the question. I mean, sleeping is sleeping. Waking up is not sleeping. Is when you stop sleeping, right?
Mhm. So basically, in the sleeping mode, you are doing no collection, no
No,
transmitting,
no,
no
no,
sending.
no. Sleep modes means sleeping. You're not doing anything. You cannot collect data. You cannot store data. You cannot transmit. You cannot receive anything. Very important.
Mhm.
You're sleeping. It's like human sleeping. Like no connection to the outside world.
Yeah, and the
When
wake
you
up.
wake up,
Yeah.
you need a little bit of time to power up everything, but then you're on. Then you're in a standby.
Okay.
Okay.
Yeah. So I think I covered all the questions, yes. And thank you, Anna, for yet another interesting talk.
It was fun again. Thank you very much for the questions and for the attention.
And I guess with this, we will wrap your lecture series on IoT, hardware, sensors, and energy. And
Correct.
we will move on to a new phase by Marco and Pietro that is more about network and technologies and so on.
Correct. Correct.
And thank you everyone for joining us. And Thank you, Anna, again for joining us in this
Thank
course.
you, and have fun with the next lectures, tutorials, workshops, and so on. Enjoy.
Yeah, thank you. Bye bye.
Bye bye.